Alright, so let's talk about the last few statistical methods that you need to understand about. So we're not actually going to go through how to do these. There's lots of information out there that you can figure out if you ever got to it, but you need to know these are out there and what they're called and when you would use them. Alright, so the non-parametric version of an ANOVA is called a Kruskal-Wallis test. Alright, so this basically is when you have non-parametric data, but you have more than two categories. So just like a t-test should only be used if you only have two groups, the Mann-Whitney U-test should also be used if you only have two groups. If you have multiple groups in parametric data, you need to use an ANOVA. If you have multiple groups in non-parametric data, you need to use a Kruskal-Wallis test. Alright, so the Kruskal-Wallis test is basically like a one-way ANOVA. So if you have one variable, but you have more than two categories, more than two test groups, if you will. So it's for non-parametric but rankable data. Right? So often this is used for data that's non-continuous, that's really hard to make continuous or to use a derived variable. So oftentimes this is for that ordinal data where you have distinct data points, where you have 2, 3, 4, 5, but you can't have 2.6 and 3.3 or whatever. You have exact numbers. Examples of that would be number of children in a household. Right? A family can have an average of 2.1 kids, but you can't actually have 2.1 kids living in the house. You have 2 kids, or you have 3 kids, and so forth. That's ordinal data. Again, you need more than 5 observations for at least one sample. Sample sizes don't need to be equal. It does not work well if you have very little difference between groups with relatively large sample size. So in other words, it doesn't work well. It's not very strong. It's very conservative. So it's not going to find small differences very easily. And this is one of the reasons you use an ANOVA if you have parametric stats. But if you can't do it, this Kruskal-Wallis test is useful. All right, so let's think about when we might use this. So here's an example. So the density of daisy plants at 4 different locations on the University of Worcester campus. All right, so basically, this might seem weird because you have number, but when you have number, you're getting the number of plants in these little areas. So you have a defined area, and you're basically figuring out how many plants are in there. Well, you can't have 14.5 plants in there, right? You can't have 20.6 plants in there. It's non-continuous data, and if it's non-continuous data, it's by default can't be parametric because you have to have interval data to be parametric. All right, so if you're using these as data points, you had 8 daisy plants, and then 9, then 9, then 12, and so forth. This is non-parametric data. But we have multiple groups because they looked at the cricket pitch, they looked at the lawn, they looked at the quadrangle, they looked at the rugby pitch. This would be useful for a Kruskal-Wallis test. All right. Another example is maybe you wish to test whether or not the drainage system from San Diego into Mission Bay has any negative effects on turtle populations. So you're testing the number of turtles swimming at 4 different locations around Mission Bay. And each of those locations has 5 different 20-meter squared sites. So within that 20-meter square area, you're going to have a certain number of turtles. You're just counting the turtles in there. Was there 13? Was there 12? Was there 2? Was there 4? Right? So unless you're getting the average at each site, and if you get the average at each site, then you can get interval data, because now you can say the average was 5.6. But as soon as you do that, you actually only have 1 data point. You took your 5 data points and you made it 1 data point. So that's where it's very difficult to use parametric stats, because you can't then go and do that replicates. So our replicates are the 5 different 20-meter squared plots at each of those locations. This is ordinal data because each of those plots cannot have half a turtle or a third of a turtle or so forth. So then we're going to compare these, and we need to use Kruskal-Wallis test because this is non-parametric data. The data is not interval, it's not continuous. Kruskal-Wallis would also be very useful for multiple groups where those groups do not fit the parametric data parameters. So if they're not a normal distribution, you would use a Kruskal-Wallis test. Right? Another thing that you can do is called Wilcoxon's matched pairs test. So remember, our Mann-Whitney U test was for data that was non-matched. This is what we use for matched test. And so example, again, remember matched means paired. And that means that you have data where it's left eye had test drops and right eye had control. Same individual, that's paired. Or before and after. Right? So the paired data means the two samples are not independent. My left eye is not independent of the right eye. I'm the same person. Or anything that's before and then after. So you did a rankings test. So maybe I did a rankings test at the beginning of the semester on what you think of me. And then after the end of the semester, I gave you that same rankings test. Those are paired data. So maybe I got a 10 because you really liked me at the beginning of the semester, and now I get a 6. Well, that's still paired data. That data is not independent of each other. Because from someone else, maybe I started off as a 2. You really didn't like me, and now I'm a 6. That ending point of a 6 is very different if I'd started off as a 10 versus if I'd started off as a 2. So those paired data means that the data are not independent of each other. And so if you have paired data, the Mann-Whitney U-test does not work well. Then you have to use what's called a Wilcoxon's matched pairs test. And if we were still doing this in class, I'd actually show you how to do this, but I know that online takes a lot longer, so this is one of the things we're going to drop. But you do still need to know what it's useful for. All right? So you have non-parametric data, data that's rankable, and the data is paired. It's matched. That's the key for this one. All right? If you have more than 2 sets of data, then you still need to go and use a Kruskal-Wallis or an ANOVA. All right. So this is kind of the summarization here. We know what a t-test is for. We have different versions of t-tests where you have equal versus unequal variance. We've learned about a z-test and an ANOVA before. Now we've added our Mann-Whitney U-test, which is for 2 groups being compared and for non-parametric but rankable data. Then we have the ANOVA, the non-parametric ANOVA called the Kruskal-Wallis test. This is when you have multiple groups, still one variable. And then we have the Wilcoxon's matched pair test. So this is when you have 2 groups, but the group is paired like we just talked about. All right? So in summary, what do I expect you to know from this second part of the semester? So we've done a lot with parametric statistics. You should be very comfortable determining if the data is parametric. In fact, I would go back and I would just practice the testing for those parameters. I would practice doing the frequency graphs. I would practice testing if 67% of your data is within 1 standard deviation. I would make sure you remember the skewness parameters and so forth. So know how to test and determine if that data is parametric. Right? And because that's more powerful and should be used whenever possible. So within that, you also need to understand what interval data is versus some of the other data. Right? You need to be able to perform a z-test, t-test, and the 2 ANOVAs using Excel. So we also spent some time practicing that parametric statistics. So these are the types of things you should also practice, and you can go just practice doing the homework again. But not only should you know how to do an ANOVA, or how to do a t-test, or how to do a 2A ANOVA using Excel, you should also remember those F-tests, all right? How do you test if the variance is close enough to really move on? So we have the F-test, and we have the F-max test, all right? So all of these things you should be able to do, and actually chi-squared is in there as well. You should be able to do using an Excel. And so remember how to format your data, remember the syntax of those commands like frequency command, the control shift enter, those weird things. I would make sure you have that in a single area that is easily accessible and you're pretty comfortable with doing that for the final exam. All right, so the non-parametric stats. All right, so we know that this must be used for the data that is proven not to be parametric. We now have the Mann-Whitney U-test. That's the one thing you should be able to perform in Excel, and within that you should be able to perform the rank averages to rank the data. Right? You should know the criteria for using all the tests that we just kind of had in the table. Z-test, t-test, chi-squared, one-way, two-way ANOVA, Mann-Whitney, the Kruskal-Wallis test, and the Wilcoxon's test. Right? And absolutely critical, when you're performing those tests, you need to be able to then tell us what it means. So if you perform an ANOVA and you get a p-value that's less than 0.05, what does that mean? Well, it means that at least one of those groups is different from the rest. Well, then how do you figure out which of those groups? Then you got to do the Tukey's test. And Remember, if you find a statistically significant difference between two groups, go back to the original data. Does it mean that this drug helped, or does it mean the drug hurt? Just because there's a difference doesn't mean it was beneficial, so you have to tie it all together like we've practiced. All right? Remember our compost data. Just because there was a difference doesn't necessarily mean the compost helped the plants grow. You have to go back and look at the data and say, oh yeah, indeed, with compost A, the plants were bigger, and therefore compost A helps. That's important. All right, then a reminder for the bioinformatics part. Most of this stuff you're going to be pretty good at just because of the proposal and things like that. But we've talked a lot about PubMed, for example. PubMed, reading a paper, I think you're going to be perfectly fine with. Remind yourself how to do a BLAST search, how to do that BLAST sequence search. That was a huge part of the first half of the semester. So just go back and redo one of those practice homeworks again. So just make sure you can put it in there, because just like the statistics, anything I give you uses the same exact sequence of events. So I can give you any sequence, and you just, as long as you know how to put it into BLAST and how to find the chromosome location and things like that, you're going to be fine. Right? We also kind of searched for protein nucleotide sequences, so those NCBI databases, kind of remember those. And then a few of the other ones just to remind yourself of. OMIM, nucleotide and protein, we've already talked about. JASPAR was that one that allows you to see what sequence a transcription factor would bind to. PDB is where you find your three-dimensional crystal structures of proteins, and we had a few things with Chimera. So just remind yourself of these things and make sure you have a convenient way to get to them if a question involves them on the final exam. And then finally, just kind of some of the generalities of science research. You're going to be fine with most of this, but by now you've searched for texts a lot. Don't forget certain syntaxes. So if you're searching for an author, remember it's last name and then the first two initials. That's the best syntax if you're searching by author. Otherwise, it's just a standard search. You guys are doing great at analyzing the literature, figures, scientific method. You guys are going to be in pretty good shape with this stuff. So this is all very well practiced. So these are just reminders of the things that you should just kind of familiarize yourself with again for the final exam. And I think you'll be in pretty good shape. All right. Don't hesitate to contact me if you have questions. The final exam is basically going to be a 3-hour exam, and you'll have some things you have to do. You can imagine you're going to have to do some statistics stuff with Excel. It's open note again, but it's one of those things that you will run out of time in 3 hours if you're looking up everything. That's why you want to practice and just make sure you know where things are at so you can locate them quickly, and hopefully make sure that you're not having to look up everything. You've practiced enough that you're pretty comfortable with the frequency function, for example. Maybe you have to look up the count-ifs term for testing if 67% is within one standard deviation. But if you have that count-ifs term, easy to get to, that's not going to take you a long time. I still have to look those up because it's not something I have memorized, but I know what I'm looking for, and I know where they're at, and I can get to them and do them pretty quickly. That's what I hope for you to be able to do, and you should be fine. All right? Ask me if you have questions. It's been an honor teaching you guys this semester. I appreciate all the hard work and efforts you've put in, especially the second half of the semester, as everything got really strange. And I haven't read your research proposals yet, but I'm definitely looking forward to them. By the time you get to this, I may have already. But I know those are going to be awesome because you guys have worked hard on those too. So thank you for everything. God bless, and good luck on the final.